Empirical research is a way of gaining knowledge by means of direct observation or experience. It is used to answer empirical questions which must be precisely defined and answerable with data. Usually, a researcher has a certain theory regarding the topic under investigation. Based on this theory, some statements or hypotheses will be proposed. From these hypotheses, predictions about specific events are derived. These predictions can then be tested with suitable experiment. Depending on the outcome of the experiment, one would know whether the theory on which the hypothesis and the predictions were based will be supported or not. The term empirical was originally used to refer to certain ancient Greek practitioners of medicine who rejected adherence to the dogmatic doctrines of the day, preferring instead to rely on the observation of phenomena as perceived in experience. Later empiricism referred to a theory of knowledge in philosophy which adheres to the principle that knowledge arises from experience and evidence gathered specifically using the senses. In scientific use, the term empirical refers to the gathering of data using only evidence that is observable by the senses, or in some cases using calibrated scientific instruments. What early philosophers described as empiricist and empirical research have in common is the dependence on observable data to formulate and test theories and come to conclusions. Usage: the researcher attempts to describe accurately the interaction between the instrument or the human senses and the entity being observed. If instrumentation is involved, the researcher is expected to calibrate his or her instrument by applying it to known standard objects and documenting the results before applying it to unknown objects. In other words, it describes the research that has not taken place before and their results. In practice, the accumulation of evidence for or against any particular theory involves planned research designs for the collection of empirical data, and academic rigor plays a large part of judging the merits of research design. Several typographies for such designs have been suggested. One of the most popular of which comes from Campbell and Stanley. They are instrumental in popularizing the widely cited distinction among pre-experimental, experimental and quasi-experimental designs, and are staunch advocates of the central role of randomized experiments in educational research. Scientific research: accurate analysis of data using standardized statistical methods in scientific studies is critical to determining the validity of empirical research. Statistical formulae such as regression, uncertainty coefficient, t-test, chi-square and various types of ANOVA analysis of variance are fundamental to forming logical and valid conclusions. If empirical data reach significance under the appropriate statistical formula, the research hypothesis is supported. If not, the null hypothesis is supported, or more correctly not rejected, meaning no effect of the independent variables was observed on the dependent variables. It is important to understand that the outcome of empirical research using statistical hypothesis testing is never proof. It can only support a hypothesis, reject it or do neither. The methods yield only probabilities. Among scientific researchers, empirical evidence as distinct from empirical research refers to objective evidence that appears the same regardless of observer. For example, a thermometer will not display different temperatures for each individual who observes it. Temperature as measured by an accurate, well calibrated thermometer is empirical evidence. By contrast, non-empirical evidence is subjective depending on the observer. Following the previous example, observer A might truthfully report that a room is warm, while observer B might truthfully report that the same room is cool, though both observe the same reading on the thermometer. The use of empirical evidence negates this effect of personal, that is, subjective experience. Ideally, empirical research yields empirical evidence which can then be analyzed for statistical significance or reported in its raw form. Empirical cycle. Shall we now discuss the empirical cycle? Empirical cycle, according to A.D. Degroot, involves the following steps. Observation, the collecting and organization of empirical facts forming hypothesis. Induction, formulating hypothesis. Deduction, deducting consequences of hypothesis as testable predictions. Testing, testing the hypothesis with new empirical material. Evaluation, this means evaluating the outcome of testing. Are you clear? There are different ways of outlining the basic method used for scientific inquiry. The scientific community and the philosophers of science generally agree on the above mentioned classification of method components. These methodological elements and organization of procedures tend to be more characteristic of natural sciences than social sciences. Nonetheless, the cycle of formulating hypothesis, testing and analyzing the results and formulating new hypothesis will resemble the cycle featured above. I suppose you have understood this. Four essential elements of a scientific method are iterations, recursions, interleavings or orderings of the following. Characterizations. What do you mean by characterization? It includes observations, definitions and measurements of the subject of inquiry. Hypothesis refers to theoretical, hypothetical explanations of observations and measurements of the subject. Predictions would include reasoning, which means logical deduction from the hypothesis or theory. Experiments mean tests of all the above. Each element of a scientific method is subject to peer review for possible mistakes. These activities do not describe all that scientists do, but apply mostly to experimental sciences, example physics, chemistry and biology. Is scientific method a recipe? Not at all. It requires intelligence, imagination and creativity. In this sense, it is not a mindless set of standards and procedures to follow, but is rather an ongoing cycle constantly developing more useful, accurate and comprehensive models and methods. I suppose you understand this. For example, when Einstein developed the special and general theories of relativity, he did not in any way refute or discount Newton's Principia. On the contrary, if the astronomically large, the vanishingly small and the extremely fast or reduced from Einstein's theories all phenomena that Newton could not have observed. Newton's equations remain. Einstein's theories are expansions and refinements of Newton's theories, and thus increase our confidence in Newton's work. A linearized pragmatic scheme of the 4 points is sometimes offered as guideline for proceeding. We have to define the question. One has to gather the information and the resources, form hypothesis, perform experiment and collect data, analyze data, interpret data and draw conclusions that serve as a starting point for a new hypothesis. Ultimately, the results have to be published. It has to be retested, frequently done by other scientists. The iterative cycle inherent in this step by step methodology goes from point 3 to 6, back to 3 again. While this schema outlines a typical hypothesis testing method, it should also be noted that a number of philosophers, historians and sociologists of science claim that such descriptions of scientific method have little relation to the ways science is actually practiced. The operational paradigm combines the concepts of operational definition, instrumentalism and utility. The essential elements of a scientific method are operations, observations, models and utility function for evaluating models. Operation. What exactly is operation? Some action done to the system being investigated. Observation actually happens when the operation is done to the system. Model is a fact, hypothesis, theory or the phenomenon itself at a certain moment. Utility function is exactly a measure of the usefulness of the model to explain, predict and control and of the cost of use of it. One of the elements of any scientific utility function is the refutability of the model. Another is its simplicity on the principle of parsimony, also known as Occam's razor. Let us now discuss characterizations. Scientific method depends upon increasingly sophisticated characterizations of the subjects of investigation. The subjects can also be called unsolved problems or the unknowns. For example, Benjamin Franklin correctly characterized St. Elmo's fire as electrical in nature, but it has taken a long series of experiments and theory to establish this. While seeking the pertinent properties of the subjects, this careful thought may also entail some definitions and observations. The observations often demand careful measurements and or counting. The systematic, careful collection of measurements or counts of relevant quantities is often the critical difference between pseudosciences such as alchemy and a science such as chemistry or biology. Scientific measurements taken are usually tabulated, graphed or mapped, and statistical manipulations such as correlation and regression performed on them. The measurements often require specialized scientific instruments such as thermometers, spectroscopes or voltmeters. Let us look into the idea of uncertainty. Measurements in scientific work are also usually accompanied by estimates of their uncertainty. The uncertainty is often estimated by making repeated measurements of the desired quantity. Counts of things such as the number of people in a nation at a particular time may also have an uncertainty due to limitations of the method used. Let me go into the definition. Measurements demand the use of operational definitions of relevant quantities. That is, a scientific quantity is described or defined by how it is measured or opposed to some more vague, inexact or idealized definition. For example, electrical current measured in amperes may be operationally defined in terms of the mass of silver deposited in a certain time on an electrode in an electrochemical device that is described in some detail. The operational definition of a thing often relies on comparisons with standards. The operational definition of mass ultimately relies on the use of an artifact such as certain kilogram or platinum, iridium kept in a laboratory. The scientific definition of a term sometimes differs substantially from its natural language usage. For example, mass and weight overlap in meaning in common discourse, but have distinct meanings in mechanics. Scientific quantities are often characterized by their units of measure, which can later be described in terms of conventional physical units when communicating the work. New theories sometimes arise upon realizing that certain terms had not previously been sufficiently clearly defined. For example, Albert Einstein's first paper on relativity begins by defining simultaneity and the means for determining length. These ideas were skipped over by Isaac Newton with "I do not define time, space, place and motion" as being well known to all. Einstein's paper then demonstrates that the absolute time and length independent of motion were approximations. Francis Crick cautions us that when characterizing a subject, however, it can be premature to define something when it remains ill understood. In Crick's study of consciousness, he actually found it easier to study awareness in the visual system rather than to study free will, for example. His cautionary example was the gene. The gene was much more poorly understood before Watson and Crick's pioneering discovery of the structure of DNA. It would have been counterproductive to spend much time on the definition of the gene before them. Hypothesis development. A hypothesis is a suggested explanation of a phenomenon, or alternately a reasoned proposal suggesting a possible correlation between or among a set of phenomena. Normally, hypotheses have the form of a mathematical model. Sometimes, but not always, they can also be formulated as existential statements, stating that some particular instance of the phenomenon being studied has some characteristic and causal explanations which have the general form of universal statements, stating that every instance of the phenomenon has a particular characteristic. Scientists are free to use whatever resources they have, their own creativity, ideas from other fields, induction, Bayesian inference and so on, to imagine possible explanation for phenomenon under study. The history of science is filled with stories of scientists claiming a flash of inspiration or a hunch, which then motivated them to look for evidence to support or refute their idea. Michael Polanyi made such creativity the centerpiece of his discussion of methodology. In general, scientists tend to look for theories that are elegant or beautiful. In contrast to the usual English use of these terms, they here refer to a theory in accordance with the known facts, which is nevertheless relatively simple and easy to handle. Occam razor serves as a rule of thumb for making these determinations. Let us now discuss predictions from hypothesis. Any useful hypothesis will enable predictions by reasoning, including deductive reasoning. It might predict the outcome of an experiment in a laboratory setting or the observation of a phenomenon in nature. The prediction can also be statistical and only talk about probabilities. It is essential that the outcome be currently unknown. Only in this case does the eventuation increase the probability that the hypothesis be true. If the outcome is already known, it is called consequence and should have already been considered while formulating the hypothesis. If the predictions are not accessible by observation or experience, the hypothesis is not yet useful for the method and must wait for others who might come afterward and perhaps rekindle its line of reasoning. For example, a new technology or theory might make the necessary experiments feasible. What are experiments? Once predictions are made, they can be tested by experiments. If test results contradict predictions, then the hypotheses are called into question and explanations may be sought. Sometimes experiments are conducted incorrectly and are at fault. If the results confirm the predictions, then the hypotheses are considered likely to be correct, but might still be wrong and are subject to further testing. The experimental control is a technique for dealing with observational error. This technique uses the contrast between multiple samples or observations under differing conditions to see what varies or what remains the same. We vary the conditions for each measurement to help isolate what has changed. Mill's canons can then help us figure out what the important factor is. Factor analysis is one of the techniques for discovering the important factor in an effect. Depending on the predictions, the experiments can have different shapes. It could be a classical experiment in a laboratory setting, a double blind study, or an archaeological excavation. Scientists assume an attitude of openness and accountability on the part of those conducting an experiment. Detailed record keeping is absolutely essential to aid in recording and reporting on the experimental results and providing evidence of effectiveness and integrity of the procedure. They will also assist in reproducing the experimental results. Evaluation and improvement. The scientific process is iterative. At any stage, it is possible to refine its accuracy and precision, so that some consideration will lead the scientist to repeat an earlier part of the process. Failure of a hypothesis to produce interesting and testable predictions may lead to reconsideration of the hypothesis or of the definition of the subject. Failure of the experiment to produce interesting results may lead the scientist to reconsidering the experimental method, the hypothesis, or the definition of the subject. What exactly is confirmation? Science is a social enterprise and scientific work tends to be accepted by the community when it has been confirmed. Crucially, experimental and theoretical results must be reproduced by others within the scientific community. To protect against bad science and fraudulent data, the governmental research granting agencies such as the National Science Foundation and science journals including Nature and Science have a policy that researchers must archive their data and methods, so other researchers can access it, test the data and methods and build on the research that has gone before. What are the models of scientific inquiry? There is what you call classical model. The classical model of scientific inquiry derives from Aristotle, who distinguished the forms of approximate and exact reasoning, set out the threefold scheme of abductive, deductive and inductive inference, and also treated the compound forms such as reasoning by analogy. In 1877, Charles Sanders Peirce framed scientific inquiry as a part of broad spectrum and as spurred, like inquiry generally, by actual doubt, not mere verbal or hyperbolic doubt, which he held to be fruitless. He outlined 4 methods of settling opinion, ordered from least to most successful. The method of tenacity, which is a policy of sticking to initial belief, which brings comforts and decisiveness, but leads to trying to ignore contrary information and others' views as if truth was intrinsically private, not public. It goes against the social impulse and easily falters, since one may well notice when another's opinion is as good as one's own initial opinion. Its successes can shine, but tend to be transitory. The method of authority, which overcomes disagreements, but sometimes brutally. Its successes can be majestic and long lived, but it cannot operate thoroughly enough to suppress doubts indefinitely, especially when people learn of other societies present and past. What do you mean by the method of congruity? It means a priori or the dilettante or what is agreeable to reason, which promotes conformity less brutally, but depends on taste and fashion in paradigms and can go in circles over time, along with barren disputation. It is more intellectual and respectable, but like the first 2 methods, sustains capricious and accidental beliefs, destining some minds to doubts. The scientific method, the method wherein inquiry regards itself as fallible and purposely tests itself and criticizes, corrects and improves itself. Ultimately, empirical research refers to the principles, procedures and processes by which we approach problems and seek solutions through verifiable data.